Welcome to Intelligent Systems, an introduction to artificial intelligence. In this video, we will look how to turn the results of a regression into a classification. And then in the second step, we will see how we turn the linearity that we had from a linear regression into non-linearity. And then basically we have all the three building blocks together to understand a neural network. So let's go back to our basic setup. A neural network is a function of w of x equals y, and it's consisting of an input layer, hidden layers, and an output. And as an example, we see here, for example, how the image with a 5 through our neural network is transformed into the output 5. Our problem was how to define that function fw, and we proceeded in 3 steps. We moved from random to optimal weights w, and this we did with gradient descent, it's sorted. But this gave us a linear regression. But we want to solve classification problems. Is this a 5 or is it not? Is it a cat or is it a dog, etc. And then of course we want to do a bit more complex things that may be not linear. So those 2 things we will achieve in this lecture. So still, we don't have the complex system of a full neural network, but we consider the simplified case in which we have 2 input neurons. One is the bias, that is with a steady x equals 1, and the other one has a proper x input. Through the weights, this gets summed up and it produces some output y. So now what we do in the first step is that we introduce the activation function h over here. And that means we change our output y from a number to a category. And then in the second step, or in the third step overall, we move from linear behavior to nonlinear behavior, and that we achieve finally by taking this basic building block and creating complexity by wiring multiple of these basic building blocks together. So let's start with step 2, moving from regression to classification. So consider this example in which we have 2 data variables, x1 and x2, and they measure results from a seismometer. So we're in the Bay Area somewhere in the US, and we have earthquakes there, but there are also explosions. And essentially our seismometer can measure the body wave magnitude and the surface wave magnitude. And if we plot those against each other, then we can clearly distinguish explosions and earthquakes. And if we put a regression line in between here to separate those 2 dots, we can clearly separate them through this line. Everything on top is earthquake, below is explosion. This line is defined by x2 being equal to 1.7 x1 minus 4.9. And now what we're going to do is we take this equation and we just reformulate a little bit. Bring everything to one side and make it equal. That gives us minus 4.9 plus 1.7 times x1 minus x2, and that equals 0. And this we write down now as vectors, simply as w times x equals 0. And w is now consisting out of a triple of minus 4.9, 1.7, minus 1. X was not a triple because we just said x1 and x2, so we introduce an artificial x0, which is always equal to 1, and then we also have a triple. So now we can distinguish earthquakes and explosion very easily with the dot product, which multiplies w and x position by position. And when the dot product of w and x is negative, represented over here, it's an earthquake. If it's positive, it's an explosion. So then we want to make this translation, and for that we use the threshold function, and that can be the step function. So we want to have a function that gets a negative value or that maps a negative value out of the dot product of w and x to a 0, which represents in our situation an earthquake, and it maps a positive value onto 1, which represents an explosion. And this can be achieved exactly by this function, which is 0 for negative values, 1 for positive values, and here we've got a jump. So essentially that means that our function fw of x becomes step of w times x. Using the mean squared errors loss function, we can compute now delta E by delta W, right? But no, there's a slight problem because the step function cannot be differentiated in 0. Over here, we cannot differentiate. So what do we do instead? So instead, we can take a continuous approximation of the step function, namely the logistic function. And it has the property that for small negative values, it is 0, and for large positive values, it's 1, and in between, we have this smooth approximation to the step function. The logistic function is defined as 1 over 1 plus e to the power of minus x. So our function now becomes fw of x equals logistic of wx. Now we can use the mean squared errors loss function, and now we're able to compute delta E by delta W. So problem solved, logistic is differentiable. Now let's do it, because the logistic function is really fun when it comes to differentiation. Because the logistic function, when differentiated, turns out to be the logistic function times 1 minus the logistic function. And let's dig a little bit deeper into this, how this is happening. So we have the delta logistic function by delta x. Now we write this out by the definition of our function, so that means we have here 1 divided by 1 plus e to the power of minus x, and we want to differentiate this now by x. So let's change the notation, and instead of the fraction over here, we write to the power of minus 1, and that gives us the second line over here. Now we can build the derivative, and that means we take minus 1 here to the front, and this becomes minus 2. But we have to apply the chain rule. That means we have to build the differentiation of this as well. So this gives us this line over here, the minus from over there, the minus 2 from over here. This stays exactly as it is. And then we have the inner derivative over here. Because this is a minus x, we get this minus, and e to the power of minus x stays. The 1 disappears because we're building the derivative by x. Now we change the notation of w, and we write this below the fraction, so the minus 2 becomes a fraction, and we remove the 2 minus symbols, so this minus cancels out that minus. So we get overall e to the power of minus x divided by 1 plus e to the power of minus x to the power of 2. Yeah, so this is this over here, and this went to the bottom of the fraction. Now, the square that we have over here can be written instead of y squared as y times y. So that's what we're going to do now. And we can also split the numerator over here, because this is 1 times e to the power of minus x. So we separate the two things. So we write e to the power of minus x divided by 1 plus e to the power of minus x times 1 plus the power of e to the minus x. And then we separate the two numerators, and that means we get 1 divided by 1 plus e to the power of minus x. And on the other side, we get this e to the power of minus x divided by 1 plus e to the power of minus x. Now, we see that in the first part, we have actually the definition of the logistic function. So that means this part over here can be written as logistic of x. But that still leaves us with that part over there. However, we can change that as well, and we do now a very old math trick that seems to be doing nothing, but that's helping us with the representation. We add plus 1 and we take off 1. So plus 1 minus 1 is 0, cancels out, so we can do that. So e to the power of minus x plus 1 minus 1, this stays the same. Now, we're changing the order in this enumerator, and we're bringing this 1 to the left of e to the power of minus x. the -1 stays where it is. So that gives us this situation over here. Now we can apply the distributive law, and we can basically separate out this 1 plus e to the power of minus x, and it's divided by 1 plus e to the power of minus x, so that becomes 1, and this -1 stays over here, and this part also stays the same, 1 plus e to the power of minus x. And again, we see this here is the definition of logistic, and overall we have found this is equal to logistic x times 1 minus logistic x. So really quite beautiful, and that means we can build our derivative. Now let's do this, and we apply as loss function now the squared error. For the moment we drop the various examples, we don't build the mean of the error, let's keep it simple. So we just have e equals y star minus logistic wx squared. So if we build the derivative by w, we get 2 times y star minus logistic wx times the inner derivative, that means minus logistic wx times 1 minus logistic wx times x. And this gives us the update rule, as you can see over here. That gets this a little bit clearer, what is what. So because we built the derivative of this quadratic term, we get this 2 times, and this stays the same, and then we have to build the inner derivative, and that's this part over here. That's where the logistic function comes in, and then we have to build the inner derivative of wx, and because we're building the derivative by w, this means we have the x over here, and the whole thing over here is the e delta e by delta w, and that means it appears over here in our update rule together with the alpha to limit the step size that we're taking when changing w. Okay, so that means we have turned now the simple regression problem into a classification problem where we get values close to 0 or close to 1 depending on whether it's the one category or rather the other. And as we mentioned in the introductory slide, there are other activation functions like similar to logistic, like tangents hyperbolicus. It has the range of 1 and -1, and it's also such a sigmoid shape as logistic. But there is something that looks a little bit more like step, and that is widely used, which is the rectified linear unit. And this is strange because tangents hyperbolicus, okay, fine, it's differentiable. We only have to change now. One class is everything close to -1, the other one is +1. But ReLU is not differentiable in 0. Over here, it has the same problem as the step function. So we discarded the step function for this reason. Why is ReLU used nonetheless? Well, the thing is, the 0 is actually rarely encountered, so the pragmatic solution for ReLU is just treat it as 0, so make it inclusive in that left part, or take it as 1, which is the gradient of this part, and just pick one of the two. And ReLU is widely used in practice because it avoids a problem that is called vanishing gradients, which means that as we add more and more layers to the neural network, the later layers have quite steep gradients where a lot is happening, but as we progress towards the beginning of the network, the gradients are vanishing. And this is a problem that is more frequent with a logistic function and less problematic with ReLU. And that's the reason why ReLU is used in practice, despite the fact that it's non-differentiable in this 0 position. Good, so that means we have solved our second problem. We have moved from regression to classification, and we got to see here now 3 activation functions that can do the job, but there are others as well possible. So we have still ignored that complex structure, but we have made our transition from this y to a classification 0, 1 through the introduction of this activation function h over here. Now let's take the final step and move from linear to nonlinear, and that means we will take the simple units that we created so far, consisting of a weighted sum and an activation, and we built them together in this more complex structure with hidden layers and various input layers and various output layers. So, and this will achieve the nonlinear behavior that we desire. But before doing so, why is it actually necessary to be able to deal with nonlinear behavior? Because we can solve so far already problems that look like this here to the right, where our data is consisting out of two classes, here the blue one and the orange one, and you can see nicely that they are well separable. But of course, we might encounter different problems which look a little bit more like this. And we can also very clearly see by eye, this is very clearly separable. The only thing is you need a line that is not linear. And that means we have to be able to create nonlinearity. And when we think of the image classification or of more complex textual vector spaces, that's absolutely clear. It's very unlikely that they have this simple linear structure. So let's move now from the simple setup to a more complex setup. And how are we going to do this? It's actually, first of all, really just an exercise in notation. We don't really do anything specific other than introducing notation for this more complex situation in where we have multiple layers. On each layer we have multiple neurons, we have weights between these neurons, and we now create a consistent naming for this situation. That's actually everything we do. So we introduce a weight WK ij, which means this weight is found in the layer K, and it's connecting the neuron in layer K-1 with a neuron J in layer K. So this is exemplified over here. In blue we have the neurons of layer K-1. In green we have the neurons of layer K, and we can label them here I from 1, 2, 3 and so on, J from 1, 2, 3 and so on. And if we dig this specific example of I and J out, we see it over here, and what we have just named is this WKIJ, which is that arrow sitting somewhere over here. Now let's also give proper names to what comes out of neuron I and what comes out of neuron J. And since the result of a neuron is the activation, we give it the name H. So H K-L is the output of neuron I on layer K-1, and HKJ is the output of neuron J on layer K. So it's essentially what we find here and what we find here. Now, how was this result of the neuron computed? Because it is the result of a weighted sum and an activation H. So let's write that up also properly. So we have the weighted sum of the inputs to neuron J in layer K, and we denote this as AKJ. So A in the layer K for the neuron J. And that essentially corresponds to the sum over all I with the weights of layer K connecting neuron I to neuron J times the H from K-1 for the neuron I. Yeah? So this part here is the output that we're receiving from neuron I in the previous layer. We're multiplying that with the correct weight and summing that up over all of the neurons in layer K-1 gives us this value AKJ. Now the activation function is common to all, and we denote it by a simple H, and that means now the output of neuron J is the result of this weighted sum after applying the activation function H. So in notation that means that HKJ, so the final output in the layer K of neuron J, is activation function H applied to the weighted sum A in layer K for neuron J. And we can basically replace the A by its definition, and that means we have the activation of the sum over all i's from the previous layer, taking the weight K between I and J, applying the output of the previous layer HK-1 I. So this sounds all complicated. We have many indices here. We have indices for the layers, we have indices for the neurons, we have weights variables, we have variables for the sum, for the activation, and so on. But in the end, it's really just notation. Conceptually, we haven't really done anything special over here. The beauty of introducing all of this notation is that now we're in a position to write down our function fwx really as the application of other functions one by one, layer by layer. So for the whole neural network, we get essentially now that we apply f to, or basically we start over here with our input x, we compute with the first layer the weighted sum, fit this into the activation function h, and move on through layer 2, 3, and so on until we apply the activation function n layer k minus 1, build the weighted sum layer k minus 1, apply the activation function again, build the weighted sum again, and this gives us the final result. This function can be differentiated because everything that we included here in this way is differentiable. And the details how we do that in backpropagation we will exercise through in the next lecture. But the key point here is through the introduction of this consistent notation, we're actually able to write the complex function fwx, which will expose nonlinear behavior through a composition of simpler functions that essentially compute the weighted sums and the activation function. And overall, this construct gives us the nonlinearity that we wanted to achieve. So how do we find now the W? And we said we do that through backpropagation. And now in the next slides, I want to show and make the point again why backpropagation through gradient descent is so important and why we can't really do without it. So consider, for example, now this simple function fwx is w1 times x1 plus w0, and we have a given step size alpha. Essentially, there are 4 possibilities in which we can change w. We can add alpha to both weights, we can deduce alpha from both weights, or we do a mixture, adding, deducing, adding, deducing. And we can simply compute all of these 4 possibilities, and then we keep the update that reduces E the most. If we would do this, there would be no differentiation, no gradients. However, there would be a problem. And the problem is a combinatorial explosion. So how many neighbors does a point have in a high-dimensional space? So as long as we're with 2 weights, it was pretty easy because there were 4 candidate adjustments that we had to consider. If we would move to 3 weights, it will become 8 possibilities. And as we move to n weights, we move to 2 to the power of n candidate adjustments. And that's clearly not feasible. So if you think of those practical examples, SimpleNet with 6 million parameters, AlexNet 60, ChatGPT with 1 trillion, this would be 2 to the power of 6 million to the power of 60 million to a power of trillion. And that combinatorial explosion is of a size that is beyond any imagination. And to make that clear, I want to give you an example. It's an old story that I think is coming from India. And I think it's very important because it documents very, very nicely how difficult it is for us to understand exponential processes and combinatorial explosions. And this story is called the second half of the chessboard, because the first half of the chessboard is still pretty reasonable, but then in the second half it just explodes. So the story is that that there is somebody, some advisor who had done something good for the king or the queen, and then they should be given a reward. And what they asked for is that a coin is placed on the first square of a chessboard, and then 2 corns on the second square, and then the following day 4 on the third, 8 on the fourth, 16 on the fifth, and so on and so on. And the king or the queen is saying, "Oh, look, dear advisor, you're not asking much. but in fact, of course, the king or the queen did not really understand this combinatorial explosion. And as long as you're in the first half of the chessboard, it's still reasonable and understandable and you can still figure it out. But once you move to the second part of the chessboard, it just explodes. And the overall amount of grains that are placed on the board is 2 to the power of 64 minus 1, and that amounts to roughly 1,600 times the world production of corn as we have it today. So essentially, the king or the queen, if they had agreed to that reward, they would have given away their kingdom. Good, and I think that's a beautiful example, and you show this is just 64, but we're dealing with 6 million, 60 million, a trillion. So it's absolutely clear this approach of really checking all of the directions in the landscape of the W's is impossible. And that's why we need backpropagation. We have to figure out through the derivative of the error function which direction gives us the steepest decline. And if we have figured out that, there is no need for us to look at all of the other neighbors. We just concentrate directly on that direction, and we can take that. And so because of this combinatorial explosion, that is the reason why we have to do gradient descent. And in order to apply the gradient descent efficiently and effectively, that is the reason why we need backpropagation. And for that reason, we need an organization to apply backpropagation. We need an organization of a neural network in layers, because we're going through layer by layer and apply the adjustments of the weights. Yeah, and then you may ask, well, hey, hang on, by the way, it's called neural network because we're dealing with neurons. So do we have in our human brain also the system of layering? So let's consider that. If we look at this situation of our artificial neural network, then essentially all of the nodes have the same number of neighbors, the same number of nodes that they connect to. So if we ignore for a moment the input vector and the output vector, and we just assume a simplified, fully connected neural network, then essentially all of the nodes have exactly the same amount of neighbors, and it's the square of all of the nodes that are in the layer. So every neuron has exactly the same number of neurons that is connected to in our artificial neural network. So, well, how is that in the brain? Do all neurons in the brain have the same degree? Now let's consider that. And the answer is, well, actually, we cannot really answer this question because we do not really know that much about the brain. And that might be quite surprising to you. So it's actually their own word for it. It's called the connectome. And that means the neurons with all of their connections in a brain. And that is an own research area within the life sciences. And as you can imagine, it's very easy for Google to work on skin diseases because you can just take a photo of your skin and then you can work on that. But working on a brain is actually something very, very difficult. And that is the reason why we actually do not know that much about the brain. However, we know quite a bit about the brain of a worm and the brain about a fruit fly. And in fact, the best we know is 1 cubic millimeter of human brain. And actually, in none of these, you will find layers. So let's look a little bit into detail into that. And all of these results are really stunning and are fairly recent. So this is the depiction of a worm called C. elegans. And this is widely studied in the life sciences because the worms are transparent, they grow very fast, so that means you can do very, very easy experiments with them. And what we're able today to do is that we can map really all of the cells that this worm consists of. It's a couple of thousand. And in fact, we can quantify also how many neurons it has. And it's around about 600. And these round about 600 neurons in the worm brain have about 7,000 connections. And that was published in a paper in Nature. That's one of the top journals to publish in. So that was really a milestone finding, published in 2019. And in the paper, you can find a plot that shows here on the x-axis the degree of the neurons, and on the y-axis the fraction of nodes. And if the worm brain was wired in the same way as our artificial neural networks would be, then essentially all of the nodes would have the same degree. That means there would be a one spot with 100% of all of the neurons. But as you can see, that's not the case. The fraction is higher for few connections, it's lower for many connections, and in that sense, the brain architecture in terms of its connections is much more similar than a network like the friendships in Facebook, or the wiring of airports and how they connected to each other, or food networks of predator and prey. And these are so-called small world networks. And these networks have the property that there are a few nodes that are highly connected and many nodes that have few connections. So think, for example, of airports. Frankfurt Airport is very highly connected. Dresden Airport does not have that many connections. Or in Facebook, some influencer has many connections, but the average person has only a handful of connections. And the worm network is much more like these networks, and that means not all nodes have the same distribution. Then very recently, in 2024, there was another Nature publication that took that to the next degree of complexity, and it looked at the Drosophila brain and mapped out 139,000 neurons with 10 to the power of 7 connections between them. And again, there is a plot in an accompanying paper. So this is on bioRxiv, also recently deposited. It's not yet reviewed, but it's a paper dedicated to nothing but the connectivity of the neurons in the Drosophila brain. And what you can see here again is the number of synapses per connection. So they count this a little bit differently. They don't do this by neuron, but they rather do this by the connections between the neurons, and they're checking how many synapses they can find there. And you can see here the number of connections plotted, and again, it's not evenly spread out, as would be the case in our fully connected artificial neural network. So again, brain of a fruit fly does not have the same architecture as our fully connected artificial neural networks. And that brings us to the human brain. So in this paper from 2005, you can find the number that the human cortex, so that's part of the brain, is consisting out of 10 billion neurons with 10 trillion connections. So really huge. And until very, very recently, the only thing we knew about the human brain was really just a mapping between roughly 1,000 brain regions. Yeah. So in terms of granularity, we're going from 10 billion neurons to just 1,000 brain regions and their connectivity. So this was published in 2008. And also between these brain regions, they mapped out these degree distribution, and you can see that also these brain regions are not evenly connected, but there is a deviation between them. However, very recently in Science, also a top journal in the life sciences this year, there was a major advance in which 1 cubic millimeter of human brain was investigated. They took 57,000 cells and they mapped out 150 million synapses between these cells. And I highly encourage you to go to the accompanying website. It's listed over here. They allow you to interactively fly through this maze of neurons and connections that you can find. And again, same story as with the other brains. When they map the number of synapses and their degree distribution, then this is also not that all of the neurons have the same degree. So what you can safely say is that natural neural networks really have a different topology and a different connectome than the artificial neural networks. And there are also many other differences that if we receive an input it's not that our whole brain is going active and is starting computing, which would be the case for artificial neural networks. So besides the basic analogy of a neuron and the firing, the activation function, and a weighted sum, besides that, there are also massive differences between a natural neural network and an artificial neural network. So take-home messages from today's lecture. You can have activation functions such as step, logistic, tangent, hyperbolicus, and ReLU, and you have to watch out for differentiation, where these two have a bit more of an advantage than this one, but nonetheless ReLU is very highly used. You should understand what backpropagation is and why we need it. You should understand how nonlinearity comes about, why do we need it, and how do we achieve it. And you should have a good understanding what is in common between artificial and natural neural networks, but also what is clearly very different between the two.